All right, so let me introduce our speaker today. It's a great pleasure to introduce Dr. Abhay Ramachandra, who is currently a postdoctoral researcher at Yale University in the biomedical engineering department. Dr. Ramachandra has his PhD from UCSD in mechanical and aerospace engineering, co-advised by Dr. Alison Marsden, who is now at Stanford, and Andrew Kahn at UCSD. Abhay works, his research is on the development of personalized models of blood flow in the heart and in the lung related to a number of cardiac and pulmonary diseases. One way to characterize the work is he's developing so-called medical digital twins, which is increasingly an exciting new technology in medicine. And there's many computational, theoretical, mathematical, and data science issues related to such models, and he'll tell us a little bit about that today. So.
Sure. Well, thanks for the introduction. And thanks for having me at the seminar today. I'm guessing you can see the screen and can hear me okay. So let's start it.
Yeah, all's good.
Thank you. So, today I'll be talking about this multi-scale computational models that I've been developing to over a period of, I guess, close to 10 years to understand vascular adaptation. I know a lot of you are not from medicine or a biology background, so I'll give a brief introduction to every problem I'm going to talk about or discuss, so that you have an understanding of the problem I'm trying to solve, and will then go into the details of the models and the methods. So in addition to building computational models, I've also developed skill set where I can do experiments and quantify structure, function, and mechanics in the vasculature. So what you're seeing on this first slide is essentially what we call a histology section of various blood vessels within the circulation. And in this case, I've used blood vessels from the murine circulation. So these are the mice blood vessels. And what you're seeing on the top is something called an EVG stain that stains for elastin, one of the constituents in the vessel wall, and it stains elastin black. Elastin gives you this ability to distend, or the elasticity to the wall, if you want to call it that. But the first three sections you're seeing on the left is for a systemic artery. The next two are for pulmonary arteries, and the last two are for veins within the thoracic region. And you clearly see, of course, each of these blood vessels have their own function within the body. The arteries have a higher pressure, they're a higher pressure system. Pulmonaries are a moderate pressure, and veins are low pressure systems and are mostly capacitance vessels. And if you look at the microstructure, you see that the amount of elastin goes down as you go down the vasculature, and the pressure reduces, and the amount of collagen goes up as a volume fraction of the wall. If you do the mechanics and look at the stress stretch curves and compute the energy associated with distending the vessel, you will see that the energy associated with distending and ascending is very high, and it drops as you go down the vasculature. Again, all of this is governed by function. Ascending has to store blood during systole, which is the initial part of your cardiac cycle. And during diastole, the later part of the cycle, it augments the flow so that the flow remains somewhat uniform throughout the cardiac cycle to the distal vasculature. So in other words, there is some fundamental laws governing how the structure is built within a vascular system. But there are a lot of cases in surgeries and pathologies where these blood vessels start experiencing hemodynamic loads or mechanics that's very different from the native environment. On this slide, I have a few examples where that happens. You have a coronary bypass surgery where a vein, which is a low flow, low pressure system, is arterial circulation. You have peripheral bypass surgery, which happens in the leg, which again has an altered hemodynamic environment for the vein. Arteriovenous fistulas, which is used in dialysis to access the blood and connect a patient to the dialysis machine, again subjects this vein to an arterial environment. Fontan procedure, a surgery to correct single ventricle patients with just half a heart, has this rewiring of the circulation so that the patient can still stay alive and has a circulating system that's functioning. Hypertension, where you increase the blood pressure in your systemic arteries and you see that the vessel wall remodels, thickens, and sometimes narrows. In Ross procedure, where you essentially take the pulmonary valve out and put it in the arterial circulation. So a lot of examples where your vessels are being subjected to this changed environment. And I've been, over the past few years, I've been trying to figure out how does the vessel adapt when it's subjected to an altered environment. So today I'll be talking about two examples, actually three. The bypass graft surgery, to talk about how models can help us answer this question. I'll talk about coronary bypass surgery, and then I'll follow it up with the Fontan procedure. I also have an interesting story on how the methods we've developed have actually helped answer important questions in a retrospective clinical trial in arteriovenous fistulas. Okay, so let's get started on the first example. And of course, in the process, I'll talk about the methods and the mathematical details too. So coronary arteries, if you're not familiar with it, are arteries that originate at the root of the aorta, just outside the aortic valve, and they wrap themselves around the heart. Their primary function is to perfuse the walls of the heart so that it can keep functioning. Now, as you get old, for various reasons, you end up with coronary artery disease, as a result of which you have occlusion and stenosis and blockages. Now, if you have multiple vessel disease, you require multiple grafts. Okay, so typically you have an option of one arterial graft, which has very good patency in the long term. But for other bypasses, you need venous grafts or some other conduit. Now, most of the synthetic grafts have terrible long-term outcomes, so the surgeons are stuck with vein grafts. So they take the saphenous vein from the leg of the patient and bypass the occlusion and create this bypass graft. This is a very common procedure, 350,000 patients in the United States alone, gold standard treatment for mitral vessel disease. But the problem is 50% of these grafts fail in less than 10 years, which means you have to do repeat procedures, which have higher morbidity, mortality associated with them. Not an ideal thing. If you know someone who's undergone bypass, the recovery is several months from the surgery, after the surgery. So you don't want repeat procedures, but the failure rates are unacceptable. So one of the first things we wanted to do was quantify the mechanics in these vessels to see if there's something happening there that will give us insights. Okay, so for that, we set up the simulation methodology pipeline. My PhD lab develops and maintains this open source code called SimVascular, which has this pipeline and the solvers associated with it. So if any of you are interested, you're welcome to take a look at it. They've looked at multiple vascular pathologies using this open source software. And of course, all the code is open source. So if you want to use any of it, you're welcome to strip parts of it away for your research. But the simulation methodology pipeline essentially starts with some form of medical images. It could be MR, it could be CT. In our case, we start with CT because they have great resolution. So we extract the center lines of the vessels. We segment out the lumen, which is the blood flowing part of the blood of the vessel, and we construct this 3D geometry by a process known as lofting. Now, of course, we want to solve this continuum on a computer, so we should discretize it. So we do something called meshing. So you discretize this continuum into a bunch of tetrahedral or quadrilateral elements. The results I'm going to show you today is using linear tetrahedral elements. And we have the ability to assign different material properties to different parts of the vasculature. Now, you require a very special set of boundary conditions when you're solving cardiovascular problems, which I will address in a couple of slides. And then we have a finite element, stabilized finite element solver, which we use to solve for fluid fields and as well as solid fields if you're doing a fluid structure interaction problem. And these are representative images that show in our pressure distribution, velocity distribution, strain distribution if you've done a fluid structure interaction. So this is a simulation methodology pipeline. Now getting into the details of the numerics and the modeling, for the fluid domain, we solve incompressible Navier-Stokes equations. It's full glory here. And for the solid domain, we use this Cauchy equation, which is in standard linear elasticity. And we have this coupled momentum method where the tractions from the solid domain enter the weak form of your fluid domain as a traction boundary condition. And you have a strong coupling at the interface in the sense that the velocities and the displacements are strongly coupled at the fluid solid interface. And we use, of course, stabilization, which is actually required if you're doing advection dominated flows using finite elements, because classical Galerkian finite elements cannot handle advection dominated flows. Also, stabilization lets you use equal interpolation functions for both pressure as well as velocity solutions. So, of course, we use one of these most commonly used generalized alpha integration schemes to match our solutions. Now, as I told you, you require special boundary conditions for cardiovascular flows. Because standard fluid mechanics has these standard Dirichlet or Neumann boundary conditions where you assign a flow or a pressure at the outlet. Now the cardiovascular system has an intelligence of its own where it can always maintain this pressure flow relationship at an outlet so that the organs can continue functioning the way they are supposed to. So in order to capture that intelligence, obviously we construct everything we can and we see on these images, but there are parts of the circulation that are not visible on these images, for which we have to use some models to model that part of the circulation. So we use this electrical analogy, where a resistor corresponds to a viscous damping, capacitance corresponds to compliance, inductance, a valve corresponds to diode like this. So essentially we have these circuit elements, we put them together in various combinations so that we can mimic the pressure flow relationships that are observed in vivo. And later I will show you a result of how this helps. But at a mathematical detail is, these are circuit elements, so they do end up being ordinary differential equations for this part of the circulation. We call them 0D models, and of course the full model is called a 3D domain. And my PhD lab came up with this amazing coupling scheme where you have information being passed between the 3D domain and the 0D domain. Of course, we have some mathematical treatment on what's the best way to set this problem up so that it's computationally tractable, as well as you have convergence in your simulations. But typically, the way I set up my problem was I would pass the flow information into this lumped parameter network, solve these ODEs, and then compute the pressures at the nodes and send it back to the 3D domain at every time step, and then do a solve for that time step at the 3D level. And so you'd essentially keep iterating through this loop till you have a converged solution, and you march through the solution until you have the full cardiac cycle simulated. Okay, so of course, we have a closed loop circulation. You have to be faithful to the physiology. So our circuit diagram is a closed loop simulation. And this was a major chunk of my PhD thesis, getting a closed loop circulation model to work and couple it with the 3D geometry. And of course, we tune these parameters to match patient-specific non-invasive values. So for these patients, I simulated 5 patients for this particular manuscript, and we had blood pressures from the clinic, stroke volumes from the clinic, a percentage cardiac output that was going into the coronary circulation. This is a heuristic metric. You also have left-right flow split if you have MR data, etc. So you could tune these parameters in the lump parameter system to match these non-invasive values. And typically, well, this was done in 2017. Probably it will be a lot quicker today because the CPUs have become faster. But we run these simulations on about 3 to 4 million linear tetrahedral elements, and these are mesh adapted. And of course, one cardiac cycle takes about 10. It used to take about 10 hours on a 96 processor cluster, but I'm sure it's much lower than that, probably close to 4 to 5 hours today. But I haven't run the simulation in a while. So what's the result from these simulations? So we simulated these using this framework. We simulated 5 patients, as you can see here, and you do see that we are able to match the clinical values pretty well, within 10% error in most of these patients. And you end up with this elaborate spatial as well as temporal distribution of clinically important metrics, such as time average wall shear stress or wall displacement. Now, you can measure pressure in the clinic, but it's very hard to measure time average wall shear stress, which is clinically more important because it dictates your endothelial cell signaling. Okay, so of course, in addition to these, we can also compute a lot of other mechanical stimuli of interest, including oscillatory shear index, pressures, stresses, etc. Okay, so this is, again, a representative waveform. One of the details I did not go over earlier was that your coronary circulation is typically out of sync with your systemic circulation, in the sense that when your systemic arteries are getting perfused, which is typically at this peak systole at 0.4 seconds, you see that the coronary flow is low during that phase. And it's only during diastole, when rest of the body is not getting perfused, that the coronary system gets majority of its flow. Okay, and these are behaviors you can capture very easily if you have a lump parameter networks. So instead of prescribing this behavior, we are able to get it naturally out of the formulation because of the way we have modeled it. Of course, we also computed other things like area prone to atherosclerosis, strains, wall shear stress, as I mentioned a minute ago. So what was a major clinical finding? We found that the veins have pathologically low wall shear stress. Now, if you look at literature, it has been shown that low wall shear stress correlates with atherosclerosis. And typically, atherosclerosis is the mode of long-term failure in these venous grafts. Okay, and this is probably for the first time we were able to quantify the in vivo mechanical stimuli in these grafts in a patient-specific setting. We also saw significant differences in areas prone to atherosclerosis. There were differences in wall strain in these grafts. Okay, so this was an exercise where we ended up quantifying mechanics in a patient-specific setting. Now, the next question was, so what does it mean for the cells? And of course, we were able to develop another model. So this model I showed you was at an organ or a tissue scale. We developed another model at a tissue and a cell scale, which I'll not be going into in the interest of time, but I can always get back to it at the end of the talk if people are interested. But a corollary to the whole project was, we, in the process of trying to solve that problem, ended up developing a framework which can actually help us with virtual surgery planning. Okay, so within vein graft surgery, there are multiple choices for surgeons to perform these surgeries. They could always take a vein and split it into a Y and connect two different targets, or they could take the same vein and connect it to multiple places so the perfusion is restored, or they can do a single bypass, from a single point on the aorta to the single point on the coronary. Now, the issue is there is no guideline on how you should be doing these surgeries. There's no systematic way to go about it, and everyone's relying on surgeons' intuition and training. And as a result, you will find conflicting evidence in literature on what's the best way to perform these surgeries. There is non-inferiority of techniques, the superiority of techniques, etc. And there's a lot of argument in the process. So we felt this would be an amazing way to demonstrate the utility of the framework. And we ended up taking 3 patients who were suitable for all the 3 different surgeries that I have listed here: a Y configuration, a sequential configuration, and a single graft. And we were virtually able to modify the configuration of the grafts within a patient. Also, we modified the diameter of the grafts, because the surgeons sometimes have the freedom to pick the vein they want to suture to a target. And by doing that, we were able to come up with a clinical guideline on what's the best way to treat, or what's the best configuration for a given patient and a given geometry. Okay, so I'll not go into the details of the guideline, but essentially, if you make the grafts too small, the wall shear stress ends up being very high, and it might lend the vein to endothelial cells to damage. The wall shear stress is too low, it can be atheroprone. So there is a sweet spot for the wall shear stress, which your models here can help determine what the right configuration would be for a given diameter of the graft. Now, the other example where this framework has been of use is in fistula surgery. Now, for people who have failing kidneys, they need to be connected to a dialysis machine so that their blood can be filtered. And the way to access the blood is something called a fistula, where they connect the vein to an artery. And one of our surgeons here at Yale had come up with a new procedure to address this issue of arteriovenous fistula failures. I mean, again, it's a vein subjected to a high flow, high pressure environment, and they fail a lot. And typically women suffer more because their fistulas don't mature as well as men because of lower cardiac outputs. But this particular surgery, the radar fistula that the surgeon had come up with, had superior outcomes. The primary and the secondary patency was far above the controls. And they were trying to figure out why that was happening in a retrospective trial. And it was actually also doing very well in women. But when they looked at animal models of this fistula surgery and looked at a bunch of biological profiles and expressions, they were unable to find a good answer. But the echo suggested that there could be a difference in hemodynamics. So I used the same framework that I showed you a few slides ago and ended up simulating the surgeries on a computer. And it turns out that it is actually the hemodynamics that's making a difference. In the new configuration that the surgeon at Yale had developed, the veins are experiencing a smaller increase in pressure. The pressures experienced by the veins are about 40 millimeter mercury here, which is about roughly 1.5 to 2 times lower than what a traditional AV fistula was, would expose the vein to. And hence it looks like hemodynamics is helping the vein adapt better. And it did help tie the loose ends in a retrospective trial. Okay, so that was the first example I wanted to talk about. So the second example has to do with single ventricle disease. Unfortunately, there is a small population of kids who are born with just half a functioning ventricle. If you look at a disease called hypoplastic left heart syndrome, these kids have very small left ventricle that's that's not functional. So they undergo a set of 3 different surgeries. One's called a BT shunt. The second one's a Glenn. Third one's a Fontan surgery. So it's three surgeries in series. And finally, the kids have to live with this conduit called Fontan. Essentially, the doctors are trying to rewire the whole circulation so that the kid or the patient can live on one functioning ventricle. And the venous return is passive into the pulmonary circulation in the surgery. Okay, so as I said, what they do is they disconnect the thoracic IVC that goes into the heart. They take this synthetic graft, which is made of Gore-Tex. I don't know how many of you are familiar with Gore-Tex, but it is what we use in making raincoats. Really, probably not the best material to put inside the body. And they connect it to the pulmonary artery here. And now the issue is, these particular grafts are synthetic grafts, and they don't grow with the kids. They're not, especially the pediatric population. So these kids have to undergo repeat surgeries often, so that the grafts can be sized according to their body size. Now, our lab, in collaboration with Dr. Chris Brewer at Nationwide Children's Hospital and Alison Marsden at Stanford, they've developed this tissue-engineered vascular graft, and of course, Toshi Shinoka, also at Nationwide, and a surgeon from Japan, where they implant this biodegradable polymer. And this is a picture of this graft implanted in the IVC circulation at 18 months. You can clearly see it has transformed into a functioning autologous vessel, into a functioning vessel. And when I say a functioning vessel, we've looked at it from a microstructure viewpoint, we've looked at it from a mechanics viewpoint, etc. And it does look like, work like, and function like a blood vessel. Now, one of the complications, so the way the system works is, the polymer is implanted initially. You have time on the x-axis, load on the y-axis. Initially, polymers bearing all the load, and then slowly the polymer degrades. The inflammation, which is caused by all these monocytes, circulating monocytes that penetrate the tissue, start depositing matrix. And subsequently, over a period of time, the inflammatory cells recruit surrounding cells, and which in turn start producing matrix, and that is what we call mechanomediated matrix. Now, one of the problems we have in the short term, in the near term, is about 25% of these cases had a primary complication, which was stenosis. Okay, so at about 6 weeks, you can see here that the diameter has become much smaller, but over a period of time, it resolves. And at 6 weeks, the clinicians tended to do an angioplasty. Okay, so this design was arrived at after a lot of trial and error, and it was yet to be optimized for multiple objectives like biomechanical properties, growth potential, stability, etc. So we felt this was an opportunity to look at modeling to answer some pressing questions. Now, what a collaborator did at Nationwide Children's was they implanted these grafts into animals. Typically they work with mice, and they found that the stenosis had to do with the macrophage concentration in the wall. So they decided to treat the amount of macrophages, or they decided to treat for macrophages. So they treated these mice with clodronate, which is a macrophage inhibitor. So they found that with the macrophage inhibitor, this is luminal diameter, with clodronate treatment, the diameter was always high. So the graft was patent. But the problem was, because you did not have macrophages, you did not have cells getting recruited, and matrix was not getting deposited in the wall. So in many ways, you have this competition happening. You need macrophages because that's what gives you the cells and the matrix or the tissues in the wall. But if you deplete macrophages, you won't get that. But if you have too much of macrophages, you end up with stenosis, and the functioning of the wall is affected by it. So how do you solve this problem? So this is obviously a problem that's ripe for systems biology. So we built this, excuse me. So we built this model, something we call biochemomechanical model of a tissue engineered vascular neo-tissue formation from a polymer scaffold. Okay, so we implant a polymer. I'll quickly walk you through this diagram. It's a very busy one. So we implant this polymer, which recruits circulating Ly6C positive and negative monocytes. Now, monocytes, as they enter into the wall, they differentiate into different types of macrophages. Also, these monocytes and macrophages recruit cells like endothelial cells, inflammatory cells into the wall, which in turn deposit inflammatory collagen as well as stress-mediated collagen. Now, of course, there's also a lot of signaling going back and forth between these cells. So for modeling purposes, we use one inflammatory, one anti-inflammatory, and one immunomodulator. Okay, sorry, was there a question? But I'll keep moving, but if there is a question, please let me know. Or feel free to stop me at any point in time. But anyway, so essentially what this systems model reduces to is a bunch of ordinary differential equations, like the ones you have at the bottom, where you have some population that's changing as a function of time that depends on the current population of some other constituents, in this case, like Ly6C negative macrophage and alternately activated macrophage. And of course, you have populations going somewhere, so they get replaced as a minus. I mean, that's modeled as minus rate times something. Okay, so obviously you have rate parameters that need to be determined. You have populations that need to be determined. And you have some inputs to the model that come from other multi-scale models, like the mass density of the polymer, the pore size evolution, the stress and the wall shear stress, for which we have measurements. So these go as inputs into the model. Okay, now if you look at the model summarized here, it's a series of about 15 to 20 ordinary differential equations. And we counted and we had a total of about 43 parameters. And we had only 18 measurements. And these are 18 measurements, we sifted through literature, all our previous work for the past 10 years, and came up with every measurement that we could use to inform the model, which are listed here. So we had a total of 18 biological measurements from multimodal data collection methodologies, and a total of about 43 parameters. Ideally, this is not how you want to do a parameter estimation, right? Because you want at least one measurement for every parameter. So in some ways, this is a data poor system. And on top of it, these are biological measurements. So there is uncertainty associated with it. There's always an error bar. They're very variable, and you need to account for it when you're modeling these. So in order to answer this question, we had some fairly good luck with this framework called the TULIP framework, which again was developed in my PhD lab with Alison Marsden, and subsequently my good friend and colleague, Daniele Schiavazzi, who's now at Notre Dame in the applied math department, has been developing and maintaining this code. So it's a software library that can do data assimilation, uncertainty quantification. So TULIP stands for the Uncertainty Library in Parameter Estimation. And it's beautifully structured in the sense that you can just pull actions and plug and play your models into the framework. And it has implementations in C++ as well as in Python. Okay, but so in order to do the estimation for our problem, I essentially used three different tools. First I did an identifiability analysis, because you have a lot of data that you have a lot of parameters, but it could be that the parameters you're trying to tune to match the data are not at all sensitive to the measurements in the first place. Now, if you're doing a Bayesian estimation, it can lead to problems because you can have parameters that are not sensitive to measurements. So you end up with weird or a wide set of distributions that still give you the same output. So we have to identify parameters that are not sensitive to outputs, which is where we use identifiability analysis. Then we used, of course, Markov chain Monte Carlo methods. There's a a method called DREAM, which is differential evolution adaptive metropolis algorithm that works pretty well for high dimensional parameter spaces and rapidly varying response surfaces and multiple minima and maxima. So we use this for our MCMC algorithm. And of course, with a combination of Bayesian and optimization techniques, which I'll elaborate on in the next few slides, we are able to determine some of these parameters. If you, of course, you would want an formal problem definition. So assume you want to estimate a set of D parameters, and it has a joint probability distribution of rho. And you have this systems information model, which takes these parameters and gives you a set of measurements that are in the space Rm. And if O are a set of outputs from the model, right? And D are a set of measurements that you got either clinically or from some biological experiment. What you're trying to optimize or what you're trying to do is reduce this error between your measurement and the output of the model. Of course, one of the major assumptions in this whole exercise is that all your error can be attributed just to parameters. And I'm not looking into errors that creep in because of model uncertainty. So all the uncertainty that has come from your measurements, clinical or biological, are captured by the variance in this. So essentially, if you do the math, the likelihood expression reduces to something like this, where you have your error term here in the exponential. We use weights to determine which of these targets are more important to hit than the others. So sometimes it so happens that we are very confident that some target needs to be hit because we are sure of the measurement, whereas in some other cases we are not. So we tune this to make sure that the important parameters are hit or important measurements are hit with this weight. But of course, if you multiply it with the with your prior distribution, you end up with a posterior, which is what we're trying to optimize for within the Bayesian framework. For identifiability analysis, I use two different techniques. One is a Fisher information matrix, where you take the derivative of your model with respect to the parameter, transpose it, and then normalize it with your diagonal covariance. We look at the dominant contributions to the null vectors in your matrix, and those are your unimportant parameters locally. Okay, or those are locally unidentifiable parameters. Now, I also run a bunch of simulations using MCMC and use this learnability metric, which is essentially 1 minus square root of your ratio of posterior marginal to prior marginal variance. And if this value tends to 1, then it's a well-learnable parameter. If it tends to 0, it's a not learnable parameter, right? So in an intuitive sense, if you've run thousands of simulations and you still see that your distributions are not changing, it means you're not learning anything about the parameter even after running thousands or tens of thousands of simulations. So those parameters, I usually put it aside because they're globally not identifiable. Okay, so once you do this identifiability analysis, so this is essentially the framework I use for parameter estimation, right? So this is my biochemomechanical systems model. I take a parameter realization, or I take the outputs, I do a Fisher information analysis, matrix analysis, and I found that 12 out of the 43 parameters are locally unidentifiable. So I fix them to a biologically reasonable value. And then I run my MCMC dream, and Gelman-Rubik convergence is one of the commonly used metrics to check if your Markov chains have converged. And if they have, then I look at the parameter means distributions. And of course, I look at the global identifiability and look at the learnability metric, do a global identifiability and find out if the parameter can be identified. So with this exercise, we were able to eliminate 9 parameters because they were not globally identifiable. So we have removed a total of 21 parameters now. And if you run estimation for rest of the parameters, and of course, the Bayesian will only give you a posterior well. If you want a maximum a maximum within the well or the hill, you need to run an optimization with the Bayesian optimum as the initial point. So we use the simple simplex algorithm like Nelda-Mead, a hill climb algorithm. And finally, you get the optimally tuned parameters, which are a total of 22 parameters out of the 43 in this whole estimation process. So if you look at the results, right? So we had a bunch of measurements, some literature experiments from the clinic, etc. And these are predictions from the simulations. And you can see that the estimation framework does a fairly good job estimating or reproducing these results or matching them within error. They're all within 10%. Okay, so the framework can match the measurements well, even in the presence of uncertainty. And of course, you determine these parameters, you put error bars on them, which are very helpful. And you can do, of course, a local sensitivity analysis to determine how much an output changes when you change an input. And you do gain some biological insights. For example, changes to your synthetic smooth muscle cell rates will make a huge difference to the amount of inflammatory collagen that's produced or the amount of smooth muscle cell that survives at 168 days, etc. Also, you notice that parameters that come later in your ordinary differential equations make little difference to a lot of these targets. Or in other ways, this gives us some insights into the system. So typically within the systems biology community, you're modeling thrombosis or some cell signaling, there's always a feedback or a feed-forward loop that's trying to keep the system in balance. But tissue engineering is a little different in the sense that you have an insight to begin with, which sets a series of events downstream. But then there is very little feedback going into the initial insight, and that kind of gives you a structure into this whole mathematical set of equations, which we haven't explored much, but we hope to in the future. And coming back to the results, again, if you can see, all the dots are the measurements that we got from the experiments, and these are time evolution or predictions from the optimal parameter sets. Okay, and again, you see that the model captures a lot of these measurements very well. In some of these, they do not capture well. For example, here, and these are these are systems in which we have a lot of parameters, but we don't have a lot of measurements. Okay, so this in turn can now inform our experimental data collection. And next time we do these experiments, I would probably make more measurements in smooth muscle cells or the endothelial cells or the synthetic smooth muscle cells. Okay, so that was one of the, those were a few insights we got from modeling. And now we have a model that has assimilated the biological data and has the predictive ability, right? Now we can start taking rational design approaches to these scaffolds as well as pharmacological interventions. Now, one of the things we explored was, what would be the effect of pore radius, because that's what you control when you manufacture these polymers. And we determined that 20 micron pore would be a good design, but with 2 micron, it would be terrible because you would have no cell infiltration whatsoever. And then, you that's not good because you won't have a functioning tissue engineered vascular graft at the end of it. Also, we can do things like dosing as well as duration of treatment. One of the treatments we looked at was a TGF-beta R1 inhibitor. So if you inhibit the TGF-beta R1 pathway, it turns out that you end up with very good outcomes in these vascular grafts. Of course, these are all parametric studies, but the plan right now is to couple it with a multi-scale model at a tissue scale, and then run formal optimization so we can come up with good designs to manufacture and implant, as well as the right pharmacotherapy for optimal long-term outcomes. Okay, so those are the two examples. I had one more, which was on vascular growth and remodeling in vein grafts, which gave us great insights and actually led us to an idea where we came up with a new medical device which can prevent vein graft surgery, but in the interest of time, I will not go into it, but I'm happy to talk about it when time permits. So to wrap up, right, what I'm hoping to accomplish during my academic career is the establishment of this accelerated translation framework. What does it entail? I've showed you, I've been trying to build these computation models. Right? They're at a cellular scale, they're at a tissue scale, they're at an organ scale. So they're multi-scale models. And of course, I'm working on coupling them now currently. So these are mechanics-based or physics-based, biology-informed multi-scale models. In addition, we have data coming from the clinic or from animal models, where using very systematic mathematical approaches, we can assimilate all this data into the model. And subsequently, you can always iterate, especially with an animal model. You can inform and validate this multi-scale model, and you can also predict and accelerate translation of technologies to the clinic. Of course, there is a lot of fundamental developments that need to happen within mathematical theories to make this happen, especially in the multi-scale coupling, because if you look at it, you're working with phenomenon that happens at a few seconds. For example, the cardiac cycle, cell signaling, which can happen in a matter of few seconds, minutes to several hours, then matrix production, which is several days to weeks, and then tissue level remodeling that you don't see for several months to years. The question is, how do you build a computational model that is robust, that converges, is faithful to biology, and is still computationally tractable and so those are challenges that I'm hoping to address through rigorous mathematical approaches. And what I'm hoping to accomplish is, with these insights, with these models, I'm hoping to gain insights into vascular adaptation, and in the process, augment or change how the adaptation happens within the current surgeries, so we have better outcomes, and also come up with newer solutions for a lot of these vascular applications. And of course, to make this happen, I need a collaborative ecosystem that has expertise in multiple tools and techniques, and obviously several departments. And one of the reasons I'm really excited about University of Florida is I think it has all the pieces that I'm looking for to make this accelerated translation framework happen. Okay, so finally, I'd like to acknowledge the labs I have worked with and my collaborators. Of course, we have had funding from multiple government agencies as well as private foundations for all the work I've showed just now, and I'm happy to take any questions at this point. Thank you.
Great, thank you, Abhay, for a fascinating talk. I think we have time for maybe a couple of quick questions.
Hey, Abhay, I have a question. Maybe I already mentioned this in the teaching philosophy talk in the morning. So here, the model, you have 43 parameters, and you mentioned that there are 18 measurements.
Right.
It still remains unclear to me how you form this identifiability. If you look at the inflammatory cells fitting and the signaling molecular fitting, there are it seems to me very few data points. So
right. So I mean, I do not have the table here that shows which of these parameters were determined, or I can pull that up quickly. But essentially, the strategy was out of the 43 parameters, that we had to eliminate 21 parameters from the estimation. Those 21 parameters were not sensitive to the measurements against which we were trying to tune the model. Okay, so in other words, the measurements were not good enough to tell us what these 21 parameters should be or could be, right? So there's nothing you can do in a scenario like that. So we had to just set it aside and fix it to biologically reasonable value. Now that can be insightful because, as I mentioned earlier, I guess with in one of the conversations, people spend a lot of time and resource trying to collect data in a clinic as well as in experiments. You know, a lot of money, a lot of time, a lot of people. But it might so happen that all that effort might go a waste because it's not going to inform your model. Right? So I guess this is one place where the identifiability analysis can help. So coming back to your question, the 21 parameters could not be determined. Okay, so there's nothing we could do, so we kept it aside. But the other 22, we tried to match these 18 measurements within this error. Okay, so this is the uncertainty in the measurement. And these are values we had from literature or our experiments that we had to match. Okay, so when we do that, it turns out that we can estimate these 22 parameters using the Bayesian and the optimization techniques. And you do see that the simulations match these 18 measurements very well. So, and that's how we determine the next 22 set of parameters.
okay. Okay, thank you.
Any other questions?
What kind of programming language are you using?
So I've used a bunch of programming languages. So the fluid structure interaction solutions I showed, it's a legacy code and most of it is in Fortran. The wrapper scripts, we've slowly translated it into C++ and Python. Okay, so essentially Python, C++, and Fortran is what I use for the fluid structure interaction problems. For this particular application, the Bayesian estimation is implemented in both C++ and Python, and I've been using those. Occasionally, if you want to prototype a new method, we start with MATLAB, but it doesn't have to be always MATLAB. If you want to scale it and make things faster, I guess Fortran and C++ are still the way to go, for us at least, with the libraries and packages we're using.
Okay, thank you.
Thank you.
All right, one more question if there's any quick ones. If not, then Abhay, thank you very much for a fascinating talk. Thank you everybody for attending.
Sure. Thanks for having me.